Page 2 of the Chapter 7 sample test. Imagine a game where you draw a random card from a deck of 52. You then replace the card and draw again. And then again. What's the probability of getting at least one ace? At least one means I'm going to get 1 or 2 or 3. The only way I don't get at least one is if every time I draw a non-ace. So 1 minus the probability of drawing no aces 3 times will give me the probability of drawing at least one. Now the probability of drawing no aces, the first time there's 48 non-ace cards, because there are 4 that are aces out of the 52. So 48 non-aces. And that's the probability of the first card being not an ace. Times 48 out of 52, because if I put it back I still have 48 out of 52. And if I do that again for the third time, the chances of getting 3 non-aces in the 3 drawings is 48 over 52 cubed. And that would be getting no aces. And 1 minus that would be getting at least one ace. And so to work that out, we would do 48 divided by 52, that's 1/13, but I'll just type it in that way. 48 divided by 52. Take that answer to the third, and I get 0.7865, which is 7. And I'll do 1 minus that, which will be 0.213. Okay. Now I made up this fictitious data for this one. I did this in class, but I'll do it here. It says make a table. So we could have either and there's a miss thing in here. A woman is elected senator or senator, or president and president, whatever. They're supposed to be the same office. Mistake. Okay. So it could be a woman, or it could not be a woman. It could be a man. And it could be Hispanic descent, or not Hispanic descent. So you always do something and its complement. Something and its complement. Now it says the probability of Hispanic, that's this whole row, is 0.45. So I put the total out here. A woman and Hispanic would be the box where they overlap. Hispanic and a woman, that's 0.25. Since these two have to add up to be 0.45, this has to be 0.20. Hispanic and a man, or not a woman. Hispanic and a woman. And the probability of a woman or Hispanic has got to be 0.8. So if this is 0.8, then this one has to be left, which has to be 0.2. That's one way to do it. Or I can say these two add up to be 0.45, and I would have to have 0.35 to make 0.8. So if I add this way, I get 0.55. If I add this way, I get 0.60. Add this way, I get 0.40. 0.60 and 0.40 add to be 1.00, or the total probability. Or 0.45 plus 0.55 is 1. So there's the table. Determine the probability of not being Hispanic. That's 0.55. Determine the probability that a man, that's this one, or a person of Hispanic descent, which is these two, is elected president or senator or whatever it should be. Well, that would be this box, and this box. 0.2, 0.4, 0.65. Okay. Number 8. How many phone numbers are possible if the area code, that's the first 3, cannot have a 0 or 1 begin with a 0 or 1? So 0 and 1 are out, that leaves only 8 digits left. But the next can have any of the 10 digits 0 through 9. The next one could have any of the 10 digits 0 through 9. Times, now we have the local area code, and it can't start with a 0, 1, so that would leave 8 and then 10 and 10. And then the number can be any 4 numbers, so there's 10 choices, 10 choices, 10 choices, 10 choices. So I got 8 times 8 times 10, 1, 2, 3, 4, 5, 6, 7, 8 times. 1, 2, 3, 4, 5, 6, 7, 8. $6,400,000,000 for phone numbers. How many distinguishable permutations of the letters of house? 5 choices for the first, times 4 choices, times 3 choices, times 2 choices, times 1 choice, which is 5 factorial, or 5p5, because we're arranging permutations, and that works out to be 120. Bookkeeper. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters, so that's 10 choices of first, 9, 8, 7, 6, 9, or 10 factorial. But since there's 2 O's, each time I put them in, I could swap them and it still look like the same one, so I have to divide by 2 factorial ways to swap the O's, 2 factorial ways to swap the K's, and then there's 3E, so that's 3 factorial. And there's not really a shortcut on this other than using factorial on your calculator, which if you did it on the calculator, you'd have to do 10 factorial divided by, and then put the denominator in parentheses, 2 factorial times 2 factorial times 3 factorial. So that would look like, on clear math, left once and I get probability, and factorial is 4, but I needed to put a number before it, and that would have been 10 factorial. I lost it. Math left 4 divided, now I have a complex denominator, so I have to group it. So parenthesis 2 math left 4, 2 factorial times 2 math left 4 times 3 factorial, 3 math left 4, close parenthesis, and we get, for the bookkeeper, 151,200 distinguishable permutations of bookkeeper, which is a lot less than the 10 factorial ways. If all the letters were different, then we would just do that, which is 30 some times bigger. Okay, 10. How many ways are there to select 3 representatives? Okay, so we don't care what order we select them in. We're not assigning them to any kind of positions. So this is a combination. From 200, we're choosing 3, which is 200 times 199 times 198, but we don't care what order, so we got to do times divided by 3 factorial. So I can either do 200 math left and CR 3, which comes out to be 1313400, or I can do 200 times 199 times 198 divided by parentheses 3 times 2 times 1, and that comes out to be the same answer. How many ways are there to select a president, vice president, and secretary from a group of 200? So we're still selecting them, but we're now arranging them into spots. So that's going to be 200 C3. And we're going to keep the arrangement, so we don't divide by P3. So we don't divide by 3 factorial, which is just 200 times 199 times 198, or 200 math, right, NPR 3. That turns out to be 7880400, and we can do it the other way. 200 times 199 times 198, same answer. 12 has a mistake in it. It says hours flown and fatality rate in miles per miles, and I don't have miles here, so let's just change the hours to miles so that we can make some sense out of this problem. So determine the fatality rate. In 2008, there was 494 fatalities in, per the miles flown, that would have been 222 million, so comma 800,000 comma, and that would be the fatality rate in fatalities per mile, but we're supposed to do it per 100,000, so we have to multiply by 100,000, and that would be fatalities per 100,000 miles. And the 5 zeros on this will cancel the 5 zeros there and leave us with 494 228, which is 2.16 fatalities per 100,000 miles flown. Now it says do the accident rate for 100,000 miles flown. And so we would do exactly the same thing, except we do the accidents, and we also do it for 2006, which was 1523 per 24 million miles times 100,000, and the 5 zeros cancel the five zeros, and it leaves 1523 divided by 240. 1523 divided by 240. So that's 6.345, so 35 accidents per 100,000 miles. 13. Discuss how the law of large numbers can lead to the faulty reasoning of the gambler's fallacy. Kind of the idea behind that is, let's say someone has been losing more than winning, so they have maybe a streak of bad luck, and they've lost 10 times out of 20, so they lost half the time. But suppose the law of large numbers says that they should win 3/4 of the time. Well, then the law of large numbers says, oh, okay, well, I should then, if I keep playing, I should get closer to 3/4, which would be 15 out of 20, or 150 out of 200, or 1,500 out of 2,000. But after if you're behind at some point, the law of large numbers says, okay, forget that. You'll still be going by the law of large numbers. What comes should come out about 3/4. And so you really don't make up on, if you have a streak of bad luck, make up on it. And that's because the probability of the next event is independent of the event you've already had. So that's what I would expect you to try to describe on that one. And 14. Give the probability distribution for the number of heads when flipping 4 fair coins. Probability of heads. So we're doing the number of heads. Could be, if I flip the coin 4 times, could get no heads, 1 head, 2 heads, 3 heads, 4 heads, and I'm supposed to give the probabilities of each of those possibilities. Now, to do that, I will draw a tree diagram so that we can see it. I could get a heads or a tail. Then I could get a head or a tail, head or tail. Then I could get a head, tail, head, tail, head, tail, head, tail. That's 3 tosses. 2 times 2 times 2 is 8 outcomes. And then I could toss it one more time. Head, tail, 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 head, tail. What's the probability of getting no heads? Well, it would be this branch, which is 1 out of the 16. So the probability of no heads is 1 out of 16. 1 head. Well, that has 1 head. That has 1 head. Let's go through here. This has no heads. This branch has 1 head. This branch has 1 head. This branch has 2 heads. This branch has tail, head, tail, tail, 1 head. This branch has tail, head, 2 heads. This has tail, head, tail, 2 heads. This has tail, head, 3 heads. And then we have head, tail, 1 head. Head, tail, head, 2. Head, tail, 2. Head, tail, head, 3. Head, tail, 2. head, head, tail, head, 3, head, 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 tail, and all 4 heads. So there's only one way out of the 16 to get no heads. 1, 2, 3, 4 ways out of the 16 to get 1 head. 2 heads happens 1, 2, 3, 4, 5, 6 ways. 6 ways out of the 16. And then 3 heads, 1, 2, 3, 4 ways out of the 16. And to get 4 heads happens only 1 out of 16. And so there's the probability distribution for getting heads on 4 flips of a coin.